So in a semiconductor material, there are two principal mechanisms by which charge carriers can move throughout a medium. They are drift and diffusion. So let's start talking about drift first. And I understand that this is largely a review. That's okay by me. So drift occurs when an electric field acts on a charged particle. So let's consider a section of wire, right? Here's just a long section of wire. And let's start with our section of wire at T is equal to 0 degrees Kelvin. And I'm choosing this particular temperature so that our free charge carriers, electrons in the case of a wire, shouldn't have any kinetic energy whatsoever, which means they should be stationary. So I'm just going to start with a bunch of random dots all over the damn place. Okay. If I'm not mistaken, I drew electrons as blue the other day, so I'm going to try to be consistent about that. So we have some number of random electrons in our wire, right? And at T is equal to 0 degrees Kelvin, everything is stationary. As our temperature increases, we should see that our free charge carriers have the ability to move because they have thermal energy, right? So what we should expect to see for a random piece of wire in and of itself is that we just have thermal motion of charge carriers, which means it's going to be randomly aligned. So I'm going to try to just draw random directions for these such that there really isn't any discernible net direction that our charge is traveling here. Okay. If we were to place this section of wire inside an electric field, or we were allowing an electric field to act on this wire, we would see that the motion of the electrons would tend to line up with the direction of the field. Because we're dealing with electrons specifically, they will align anti-parallel to the field. So parallel, but in the opposite direction. Whereas if we were dealing with positively charged charge carriers, they would line up parallel with the field. Okay. So an electric field acts on charge carriers with this drift equation, where we're going to say our current density function, J drift, this is a vector, will be equal to Q times N times mu times E. Okay. Where, just to rehash some things I think we covered the other day, Q is the charge of an electron. Negative 1.602 times 10 to the negative 19 coulombs. N here is the electron concentration. Measured in per centimeters cubed. Mu, let me make this line go out further. In this case is our electron mobility. I'm just going to put carrier mobility here since we aren't specifying anything, but since we're looking at a wire, our carriers are electrons. This is measured in centimeters squared per volt seconds. And then lastly, we have our electric field strength. measured in volts per meter, right? So we can see from this relationship here, we're dealing with vector quantities, and so our directions are taken care of us. Our directions are taken care of for us, right? So because the charge of an electron is negative, we see that our current density is actually going to be in the opposite direction of our applied electric field. Whereas if we were dealing with positive charge carriers, we would see that our current density would be in the same direction as our electric field and all of that kind of good stuff. So the last two variables in our drift current density equation, and by the way, before I get into this, this is just Ohm's law, by the way. Yeah. So the last two terms in this equation are what are known as our carrier velocities, or the drift velocities of the carrier. And they are the average velocity attained by charged particles in a material due to an applied electric field. So this isn't the maximum value. We can have some charged particles that are traveling faster, some that are traveling slower. This is just representing our average, okay? So in a semiconductor material where we have both electrons and holes present, we are going to have an electron velocity V sub E that is equal to negative mu sub n times E. And this is just in meters per second. I'm going to change my subscript here. Sorry, in my notes I have E and H, but we're going to be dealing with things concerning electrons have a subscript of N, and things concerning holes have a subscript of P. I don't know why I was inconsistent here, so I'm just going to fix that inconsistency so that it's not weird. So let's call this V sub N and V sub P, because we're not going to talk about phase velocity and group velocity and things like that in this class, so the subscript P isn't going to mess anything up in here. So V sub P is going to be positive mu sub P times E. And this is our hole velocity. So in a semiconductor, our drift equation will have contributions from both electrons and holes. So our total drift current density will be J drift for electrons plus J drift for holes, which comes out to be negative Q sub E, the charge of an electron, N mu N E, plus Q sub P, the charge of a proton, P mu P E, trying to take into account here that these two things are going to be flowing in opposite directions. This is going to be more formally written as Q times N mu sub N plus P mu sub P times E, where we're effectively getting rid of the negative sign by observing that they're flowing in opposite directions. And we learned in our last class meeting that this guy right here is just our conductivity, electrical conductivity. And so we simply have conductivity times electric field is equal to drift current density. And literally, if we recognize that we multiply both sides by area and recognize that our electric field strength is volts per unit length, and that 1 over sigma is equal to the resistivity, this literally gives us Ohm's law. Okay. Right. So let's work a quick example here. Let's say that we have an N-type chunk of silicon where our donor concentration is 10 to the 15 donor atoms per cubic centimeter. So an N-type silicon bar with dimensions of height is 1 centimeter, width is 1 centimeter, and length is 10 centimeter. Has a voltage of 10 volts applied across it as shown below. So let's call this dimension the width, this dimension the length, this dimension the height. And we apply an electric potential of 10 volts across the length of the bar like so. If our electron mobility for this doped semiconductor material is 1,250 centimeters squared per volt second, and our hole mobility, actually I don't know why I said UN, because this should be UN. Our hole mobility is 500 centimeters squared per volt second. Then I want us to find the total drift current flowing through the bar. So J drift total will be equal to what? We're going to use Q is equal to 1.6 times 10 to the 19. So we're going to introduce a little bit of error by using a simplified version. And our intrinsic concentration for silicon will be 1.0 times 10 to the 10 per cubic centimeter. So we're effectively assuming we're somewhere in the ballpark of room temperature for this system, right? So using our equation, we know that our total drift current density should be charge times N mu sub N plus P mu sub P times E, right? So we know Q, we know both of our mu's. How do we figure out N, P, and E? What was that? So E is measured in volts per centimeter, sure. So what would I do to find E? Yeah, so the 10 volts divided by the length of the bar is going to give me my electric field strength across the bar. Absolutely. So E is just going to be V divided by L. So 10 volts divided by 10 centimeters is 1 volt per centimeter. Okay, that seems like a reasonable thing for an electric field strength. Kind of weak field, but that's okay. What about N and P? Is this an intrinsic semiconductor? It is not. Absolutely right. So because we're dealing with donor dopants and ND is much greater than NI, it's 100,000 times more, we can say that a pretty reasonable or actually extremely good approximation for the electron concentration in this bar would be just ND, right? So N will be approximately equal to ND, which is 10 to the 15 electrons per cubic centimeter. What should P be? Our whole concentration. Ni squared over ND, right? So that'll be 1 times 10 to the 10 per cubic centimeter squared divided by 1 times, let's just do it as 10 to the 15. That's just wasting time. And this comes out to be 10 to the 5 holes per cubic centimeter. Plugging all of this stuff in, we find that our total drift current is going to be 1.6 times 10 to the negative 19 coulombs times N 10 to the 15 per cubic centimeter times our 1250 centimeters squared per volt second plus 10 to the 5 per cubic centimeter times 500 centimeters squared per volt second. All of this multiplied by 1 volt per centimeter. So if we look at our units for this thing, right? So looking at our units here, we have centimeter to the -3 times centimeter to the +2. So that's going to look like centimeter to the -1, right? Multiplied by this per centimeter out here is going to give us centimeters to the -2 or something per centimeter squared. I think this volt here is going to cancel this volt and this volt because we could add these quantities together. So the volts go away. So we're going to be left with coulombs per second per centimeter squared. Coulomb per second is an amp, so amps per centimeter squared. We absolutely have the dimensions correct for a current density. This is going to come out to be 200 milliamps per centimeter squared. Now, realistically, did we need to do all of this? No. Why no? Exactly right. Yeah, so this guy right here is 10 billion times smaller than this guy right here. So it's contributing nothing. So realistically, if we wanted to know what our drift current density is in an N-type material, we really need to only pay attention to what the electrons are doing. Transversely, if we wanted to calculate our drift current density in a P-type material, realistically, we only need to pay attention to what the holes are doing because the contribution from the minority carrier is going to be so small as to be negligible. Okay? Absolutely right. All right, so this is drift current. Now let's talk about diffusion. So carrier diffusion occurs when there are variations in the carrier concentration across a medium, meaning that we need to observe a concentration gradient, okay? So the most simple example of what I can think of how to describe diffusion is mildly vulgar, but bear with me. Let's say that I stood here at this podium and farted. How long would it take Cameron to smell it? That's a function of diffusion because there would be a concentration gradient of poop particles from my pants that will gradually move across the room because of that concentration gradient, right? That is just diffusion in a vulgar form. We're talking about the exact same thing in semiconductors, but we're talking about concentration gradients of electrons and holes that are position dependent, okay? So the mathematical equation that describes diffusion is what's called Fick's law. And Fick's law says that a diffusion current density, J diffusion, is equal to Q, our elementary charge, times D sub n, where D sub n is the electron diffusion coefficient, measured in centimeters squared per second, times the derivative of our electron concentration as a function of position. I'm arbitrarily just calling this spatial variation x, okay? Minus d sub p, which is our whole diffusion coefficient. Bless you. Also measured in centimeters squared per second, times the derivative of our whole concentration as a function of position. Anybody have is my penmanship too shitty? Yeah, centimeters squared per second. So very similar to our coefficients, our mobility coefficients, except that there's no voltage in the denominator. So let's apply this guy, okay? So let's say that we have our exact same silicon block from before. So N-type with ND is equal to 10 to the 15 per cubic centimeter. Silicon bar with dimensions H is equal to 1 centimeter, W is equal to 1 centimeter, excuse me. And L is equal to 10 centimeters. Is irradiated such that electron hole pairs are optically generated on the left side of the bar. So we have something like this. We have a bar. This is 0. This is L. This is our X direction. We are shining some sort of light onto the left end of the bar, imparting charge carriers in that area, enough energy to get up into the conduction band. Gabriel, what's up? EHP, electron hole pair. So if the total carrier concentrations are given by n as a function of x will be equal to 10 to the 17 electrons per cubic centimeter times e to the negative x over lowercase ld. We'll talk about what this means. So LD is going to be the diffusion length for these electrons. So this is the average distance that they travel before recombining with a wandering hole. It's related to mean free path and all that kind of good stuff that you guys will probably talk about in 334, and we'll talk about more in this class when we get into junctions specifically. Plus our donor concentration. And then our hole concentration, P of X, is going to be 10 to the 17 holes per cubic centimeter, e to the negative x over LD, plus Ni squared over ND. So we have a spatial variation here. The left-hand term is our optically excited electron hole pairs. That's the reason why there's the same number amount. We can't generate an electron without also generating a hole, so they come in pairs. And then over here, we have our free charge carriers due to this crystal being at a certain temperature and being doped in this particular way. We want to figure out what our diffusion current density is. If dN is 32.375 centimeters squared per second, dP is 12.95 centimeters squared per second, and our diffusion length LD 2,500 microns. So our diffusion current density, J diff, our equation is Q times dN, the derivative of n of x with respect to x, minus d sub p, the derivative of p of x with respect to x, like so. Q is 1.6 times 10 to the negative 19 coulombs. The derivative of both of these expressions are going to be the same, right? Because the derivative of this constant stuff outside is going to be 0 because these aren't position dependent. So we're really only going to be looking at the derivative of this guy and the derivative of this guy, and they're literally the exact same expression. So I'm actually just going to lump my two diffusion coefficients together, right? So that's going to look like 32.375 centimeters squared per second minus 12.95 centimeters squared per second. Now I'm going to take the derivative of that thing. So I'm taking the derivative of 10 to the 17 per cubic centimeter e to the negative x over LD. So when I'm taking the derivative of an exponential function, I just bring alpha out. In this case, alpha is negative 1 over LD. Okay. So negative 1 over 2,500 microns. So what would 2,500 microns be expressed in centimeters, since our concentrations are expressed in centimeters? 2,500 microns is 2.5 millimeters. So that should be 0.25 centimeters, right? Micron is 10 to the negative 6, millimeters 10 to the minus 3, centimeters 10 to the minus 2. So it should all work out that way. Then we have our 10 to the 17 per cubic centimeter, and finally e to the negative x over LD. Since we're not trying to find this thing at any specific distance away from our left-hand edge, we're just going to get a function. Putting all of this together, we wind up getting negative 1.243 e to the negative x over LD amps per centimeter squared. So effectively, or actually, I'm going to ask you guys to explain this. Why does my diffusion current density have a negative sign? Let's look back at our picture. Right. Well, okay, so I guess a better question would be, what is the physical interpretation of our diffusion current density having a negative sign? Yes, sir. Where's an electric field here? Oh, there's no electric field in this system at all, maybe. There we go. So we have defined our positive direction as to the right, right? Our electrons are diffusing from left to right, and our electrons have a larger diffusion coefficient than our holes do, which means more electrons are moving from left to right than there are holes moving from left to right. Both of the charge carriers are going to move from the high concentration area, which is the left-hand edge of the crystal, towards the low concentration area, the right-hand edge of the crystal. So both charge carriers are going to move from left to right, but because holes diffuse more quickly, our diffusion coefficient is larger, we're going to see a larger movement of electrons from left to right than we see holes, which means we're going to have a net current flowing from right to left. Absolutely right. That's great job. Any of you look perturbed? So positive current positive conventional current is always opposite electron flow. But our next current in this system could have been positive if our hole diffusion coefficient were larger than our electron diffusion coefficient. Right? Because then, if the hole diffusion coefficient were larger than the electron diffusion coefficient, this term minus this term would have been negative, would have been multiplied by this negative term right here, giving us a positive result overall. So what you had suggested, it's just opposite electrons, is true, but it's really only true for this particular case where the electron coefficient, diffusion coefficient was larger than the hole diffusion coefficient, which should practically always be true, but just in case I throw you a curveball problem where it isn't, just for mathematical sake, I want you to have some understanding of what the physical interpretation of our results mean, because we're going to spend a whole lot of time, particularly when we look at how p-n junction behaves and how bipolar junction transitions behaves, trying to wrap our head around what the movement of all of our charge carriers doing has, like what the effect all of that charge carrier movement has on how our devices electrically operate. So I'm just trying to prime the pump, so to speak, about thinking about what these negative signs mean in a physical context. All right. So we've looked at carrier drift. Now we've looked at carrier diffusion. The last thing that I want to talk about here before we leave is the Einstein relationship that relates these two quantities. Okay. So even though carrier drift and carrier diffusion occur for completely different reasons, right? Drift occurs only in the presence of an external electrical field. Diffusion only occurs in the presence of a concentration gradient. These two different types of movement are related to each other, okay? So our Einstein relationships are as follows. The ratio of our hole diffusion coefficient divided by our electron mobility is equal to kBT over Q. And similarly, our hole diffusion coefficient divided by our hole mobility is equal to kBT over Q. And I have a note here that's effectively telling me that I made a small mistake in our last lecture, so let's go ahead and rectify this. Okay. So in Wednesday's lecture, I erroneously said that kBT was approximately equal to 26 millivolts, and that's not correct. kBT over Q is. That's it. So kBT over Q is our thermal voltage. And that's the thing that we're going to wind up seeing most of the time anyway. So I apologize for that mistake. It's been 2 years since I taught this. All right. That is enough out of me for today. So at this point in time, you should be able to work all of homework set number 1. So start working on homework set number 1. Yes, sir. So none of this depends on the cross-sectional area whatsoever. So no. Like the height and the width of the medium in a like an integrated circuit or something like that, like it's not going to affect the drift current or the diffusion current, but it is going to affect how much current the medium can actually handle. So there's a thing called electromigration, which effectively means if you try to push too much current through a trace that's too small, it melts or distorts the trace. We're not really going to worry about that too much in the context of this class, but if you choose to go look at the integrated circuits class next year, that will be a thing. So for the most part, at least in electrical engineering 335, I'm only going to be really concerned about discrete electronic circuits, meaning that it's made of physical transistors, resistors, capacitors, and all of that kind of stuff to form a circuit. So like you could breadboard it. Once we get into 336, I'll start leaning more towards integrated circuit type circuits, because they're going to necessitate us having transistor matching and things like that, that are really, really hard to do with discrete components. But from an integrated circuit perspective, that's just how we design things to function. So, did that answer your question? Probably more than that. Oh, yeah. Okay. Yes, ma'am. Mm-hmm. So drift current density way back here. Okay. So charge of an electron is a negative quantity. We have this negative sign here so that our net drift current is all flowing in the same direction. So this negative sign times the inherent negative sign here leaves us with just a Q as positive 1.6 times 10 to the 19 as a quantity. Yeah. Yeah. So electrons are flowing in the opposite direction as holes. Because this charge is negative, the two negative signs cancel each other out, and we get a nice sweep for the package. Anything else? All right, go grab lunch before your next class.